Hello, I am Kevin Treader, product marketer with Microchip Technologies' amplifier product line. In a past Amp-titudes video, we explored electromagnetic interference, or EMI, and what is being done within amplifiers to combat its adverse effects. This video is a follow-up to that conversation, in which we will utilize this demonstration platform to highlight the effects of high-frequency interference on an amplifier circuit. As a recap, EMI is a high-frequency disturbance that can affect any electrical system. EMI affects amplifier circuits by causing a shift in the offset voltage, which causes performance degradation. Now, one common question that we get is why be concerned with high frequency, perhaps 400 megahertz, 900 megahertz, and higher, when working with amplifiers that have a bandwidth well below this range? This is a very reasonable question, but keep in mind that virtually all integrated circuit amplifiers have ESD protection diodes on the input pins. These diodes can rectify these high-frequency signals, causing a shift in the input signal. Therefore, EMI and RF are always a concern, regardless of the bandwidth of the actual amplifier. It should also be noted that all amplifiers inherently have some level of high-frequency rejection. The input impedance and parasitic capacitance on the inputs form a low-pass filter function. But is this level of EMI rejection enough? What else can be done to minimize the adverse effects of EMI? This demonstration platform highlights three potential options. Option 1 is to rely on the inherent EMI rejection of a standard amplifier, in this case using the MCP6401 operational amplifier. Option 2 is to implement a low-pass filter external to the op-amp. The final option is to utilize an amplifier with an on-chip EMI filter. This demonstration uses the MCP6421 operational amplifier, which features an integrated second-order filter on the input pins to enhance EMI rejection. Now let's compare the performance of these three options. A 500 Hz sine wave is connected to the input of all three op-amp circuits. In addition, there is an RF noise source generating a 433 MHz signal with a 5 kHz square wave input. Now let's look at the results of each of these op-amp circuits and see how well they reject the 433 MHz interference signal. Let's start with the first option, which is using a standard amplifier with no additional filtering. The resulting 500 Hz sine wave shows significant shifts due to the high-frequency interference signal. Now let's switch over to option 2, which implements an external low-pass filter. Although better than the first option, we can still see significant interference on the sine wave. Finally, let's look at option 3, which utilizes the MCP6421, which has on-chip low-pass filters to minimize EMI. As you can see, the interference caused by the 433 MHz signal is reduced significantly. What this demonstrates is that the adverse effects of high-frequency signals can be reduced with the use of external filters. However, the use of amplifiers with on-chip EMI filtering may provide the best results and minimizes the footprint and component count of the overall circuit. For more information regarding electromagnetic interference and to explore solutions for minimizing the adverse effects, I recommend the application note AN1767 published by Microchip Technology. Until next time, thank you for joining me for this edition of Amp-titudes.